What's up? Hey, welcome to the JavaScript game stream. It's another exciting episode. You're here with your friend Zero Cool, also known as Pat, and this is what we did last time, in case you weren't here. It was kind of fun. We worked on this snow simulator thing, and it turned out pretty interesting. I've made just a couple changes since then. But basically the idea is that we can add or remove these little windfluencer guys, and it kind of influences the wind. So that was neat. But we're not here to talk about that this evening. Today we're here to talk about a code signal challenge. It's one that I think is pretty interesting. I guess we'll switch over to it right now. So here it is. So this one is kPalindromeWithCentre, and basically the idea is that actually, hold on a sec. Let me just switch the view for a sec. Just a second. We'll be right back. Okay. Whoops. Okay. How does that look? Hopefully okay. Hopefully the text is big enough. Anyway, if anyone has any questions, comments, concerns about the appearance or content of the stream, hey, feel free to let me know. That's part of why we're here, right? Anyway, the main event tonight is going to be this thing. I had a user request a solution to this one, and it is kind of a challenging problem. I know I definitely had some difficulties with it, so I think it's worth it for us to discuss it. So, I guess we might as well start with what the question is asking. We have a fairly extensive description over here that we'll take a look at, but it's kind of making a reference to another challenge that we've seen before. So it's referring to this kPalindromes one. I'm not going to click on it right now because it's going to link us to the interview task, and I don't want to get distracted with that. Maybe we'll solve it one day on the Code Signal live stream, but for now, we're just going to stick with this guy. We're not going to actually look at the interview practice problem that's kind of related to it. At least it can be related to it. You can look at it in a slightly different way, but it is, yeah, very much the same sort of thing. We're talking about kPalindromes. So first of all, what's a kPalindrome? We should probably talk about that. Basically, a palindrome, first of all, is something that's read the same left to right, like race car or taco cat, or there are lots of examples. Never odd or even. Anyway, the point is, so we want to make this thing. We're starting with a string. We want to make it into a palindrome by removing at most k characters from it. So k is going to be an integer. Maybe it's 5. And we basically want to, in the other problem, we want to say if the thing that we're given is a k palindrome. So if k was 5 and we're given this string, we would want to be able to tell, like, well, would it be possible to just remove at most 5 characters and have a resulting palindrome here? That's basically what the original kPalindrome problem is all about. But this kPalindrome problem is a little bit different in the sense that we get the center of it. I'm unclear maybe right at first if that makes the problem easier or harder. I actually thought it would make it quite a bit easier, and I was sort of surprised by how much it didn't really. It feels about the same as the original problem, to be honest. Anyway, yeah, we might as well keep going here, see what the problem's asking. So basically the center is going to be the index of the character that we want to be, at the center of the palindrome. So for example, in this case, we're saying the center is index 1. So this character right here, the E, we want for that to be at the center of our resulting palindrome. So in this case, the H and the Y are both just going to have to go. It's not going to match up otherwise. So it's just going to be a single E. The 2 here refers to the number of deletions or removals that we need to make. So we need to remove 2 characters from this one, and that's like the minimum we'd be able to do and still have this thing be a palindrome. So the answer is 2. And that's, I guess I didn't really get to that, but that's what the question is asking. It's basically saying, what is the lowest value of k such that this thing is actually going to be a k palindrome? Okay, so continuing with this, basically the idea from here is that, I guess we should talk about the center. So like in this case, the E was right at the center of the word. In the next case, so like 2 is the index of the thing we need at the center over here, and let's just get a little more room. Yeah, so 2 is the center right here. We need the F to be in the middle. Something to notice immediately about this one is on the left side of the F, there are only 2 characters. So it's not like we're going to be able to get more than 2 characters to the right. But actually, we're not even going to be able to get 2 characters to the right. We have the E that we need to match up, but we don't have another F. But that's okay. We can use this F because, as it says over here, basically the idea is that if the palindrome resulting from this has an even number of characters, we just need to make sure that the character at the center index is one of those middle characters. It's okay if it's... as long as it's not like way outside the center, as long as it's one of the 2 ones in the middle, then we accept it. Because otherwise, like, what would he even represent for an even length palindrome? So this is basically a way of just admitting the possibility of an even length palindrome. So it doesn't have to be odd with this character uniquely in the center. Anyway, what else? So yeah, center is basically in the original string. Like, for example, in this case, we're deleting elements from the left and right. So the resulting palindrome would only have 1 character. So therefore, the only valid index for that character would be 0. But notice when we're talking about the center, we're talking about its index in the original string, not the palindrome resulting from removing some of the characters. So that's one point of clarification. The next thing is that... like, regardless of what this one looks like, that's not going to be the thing that's influencing whether there's an even or odd number of characters in the resulting palindrome. So we don't know just by looking at it whether it's going to be even or odd, whether this is going to be like, whether the E is going to be the unique central element, or whether it's going to be one among 2 central elements. The final clarification here, and this is kind of an important note, we can't actually remove the center character. I guess that might be obvious, but anyway, it's worth mentioning. Okay, so let's continue with this stuff. I guess we want to talk about how to actually solve the problem. We've kind of gone through the first 2 examples here, so I might as well just scroll down and get caught up over here. Yeah, so kind of like what we talked about, in this case, we'd have to remove these 4 characters, so the answer is 4. We have E, F, F, E as our resulting thing. The next one, list of datas, we want the center to be the element at index 7. So let's see, 0, 1, 2, 3, 4, 5, 6, 7. The 7 is the A, or the character at index 7 is the A over here, the first A. So again, if we look at the right side here, there are only 3 characters that we can possibly use. There's no A on the left side, which means I don't know. We might not be able to make that one match up. We might have to remove that A. In fact, we definitely have to remove that A. I guess you could look at it and say, like, can we just use the S here and make it like SATAS? The thing about that is it wouldn't be centered at the A over here, so no, we can't do that. But what we could do is form the word stats, and it sort of shows us how we could do that over here. By removing a total of 6 characters. So we still have those 5 remaining. Okay, and importantly, stats would have this A at the center of it. Yeah. Okay, so basically those are examples. That's essentially what we want to do in the problem. So, I mean, we could kind of brainstorm ways that we could solve this one. The main thing is that if we're looking at this, then basically we can sort of look at it, and this was kind of the intention for having the center part of it. We could sort of say, like, all right, this thing has like the middle character, which is this one right here. I should have used a smaller size for that, but oh well. And then from there, we can sort of say, okay, so that gives us like this substring over here, and then this substring over here. And we're basically just trying to match up, like on the left and right substrings here. We're trying to find, essentially, if we were to reverse one of them anyway, we're looking for the longest common subsequence of characters. So this is actually a kind of a classic problem in computing. So let's take a look at what Wikipedia has to say about it. So here we are on the longest common subsequence problem page. I have this one open already, as you can see. We'll just zoom in a little bit. So what they essentially recommend here is that we use a dynamic programming strategy. And that's very common, that we're going to use dynamic programming. Usually this would be a 2-dimensional array kind of territory that we would use. They actually give us like a really excellent breakdown of how we would do that. So we can kind of get the flavor of the dynamic programming just from this, that, you know, we have this 2-dimensional array or matrix of values. And we're storing all of this stuff just so that we don't have to repeat subproblems, like overlapping subproblems. And then basically by the time we get to the end, that's when we normally would get like the value that represents our final answer and we're done. We don't really use any of the in-between stuff in the very end. You know, we don't actually return that stuff. We don't need to like keep this array. But hey, maybe if we were trying to find like multiple same things, like this is a possibility, right? I think the last one of these that we did, like what was it called? Like ways to make change or something like that. Yeah, for that one, we did end up reusing a lot of the values in our dynamic programming array. So that was like pretty worthwhile, you know? Anyway, going back to this one, I'm actually not going to use that dynamic programming strategy, which seems a little weird, I guess, but I'm going to try to be clear about the reason why I'm not going to use it. So I'm going to go ahead and just try to whip up a brute force solution over here. So we're going to use recursion, just classic unmemoized recursion. So we'll write a function to begin with. Maybe eventually we'll sort of convert this, like rearrange in such a way that the only function we're going to use is this one, and it'll just keep calling itself recursively. But for now, we'll make a function called search, I guess, and destroy, and it's gonna have like a left pointer, it's gonna have a right pointer, and for now I guess that's gonna be it. Okay, so it's gonna be this thing, and I'm specifically gonna actually give some default values here. So I'm gonna say the left pointer is gonna start at 0, and that the right pointer is gonna start at the right end of the string. So this is maybe starting to seem less like a dynamic programming strategy and more like a two-pointer strategy, which we've kind of seen before. So yeah, we'll see. I mean, I don't know if this is exactly going to be like two pointers. Normally with two pointers, the idea is that they kind of move independently of each other, thus avoiding like a quadratic complexity kind of situation. I don't think this is going to be exactly the same as that, but it'll have in common with those kind of problems the idea that we're using these two variables to represent different indices with, within the same string. Okay, cool. So what do we want to be doing with this thing? Well, I guess we have a few possibilities here. So notice we're starting left and right both at the edges. I guess another way we could do it would be to start them both right at the center and then work outward from there. But instead, I'm going to start them both at the opposite ends and we're going to work inward from there. And essentially what we'll do is we'll say like, well, if left has made it to center, then, do something. I guess that needs to be on another line. So let's go ahead and do that. Okay, come on. There we go. Otherwise, if that's not the case, we'll say, all right, cool. Well, if R is center, well then, yeah, also do something. And otherwise, we're basically going to do the recursive step, right? Recursive steps. Basically, the idea is that left can't go right of the center. Right can't go left of the center. So as soon as, like, these two things represent our two possibilities for endpoints. When left reaches this point, it's all over. We're not going to be able to keep left iterating. So basically what we'll do, to be more specific about this, I guess, instead of just do something, we're going to say search from the right to see if we can find a matching character. Okay, and that's not really super clear right now, but hopefully it'll become more clear as we proceed here. In this case, we're going to search from the left to see if we can find a matching character. Basically, the reason I'm talking about this whole thing about finding a matching character is because we could, for example, well, okay, I don't want to reveal too much here, but basically what it's going to address is the possibility that we have two central elements in the resulting palindrome. That's what this stuff is going to do. But what's more interesting probably is the recursive step. I mean, essentially this stuff up here is just handling the base cases. So we want to see what's going to happen when we actually get into a situation here where we have to do recursion. So I'm going to start this out actually before anything by saying let deletions be assigned the value of 0. And this is ultimately the thing that we're going to be returning at the end of this function. We're going to be calling this function right here. And notice we don't really need to give it any arguments or anything like that because it's kind of taken care of over here. You know, we have default values for these. We don't have to do it this way. We could instead pop them in here. But the reason I kind of like to do it like this right off the bat is because it's going to make it easier for us to transition into the situation where we're actually using kPalindromeWithCentre as our recursive function as opposed to this search function as our recursive function. Okay, so what is the actual recursive step? Recursive step. Anyway, the point is, for this point, this is where we actually want to like call the search function again, right? Is the idea. So we're going to say this. We're going to have two possibilities in here. We're either going to have like the two characters matching up, in which case, great. Like we can match those up. Say, all right, for example, if our left pointer is over here. Hold on. We have the tools to make this so much more visual than that. Let's go ahead and take advantage of those. Let's go with a cool kind of minty green. And there we go. I'll just grab the tablet, I guess. Thanks again to codesignal for this. All right, so here, let's say this is our left pointer. That's what it's pointing to, the S over there. And then let's say this one over here is our right pointer. So in this case, we might say, well, hey, look, like you got an S over here, you got an S over here. These two things match. We could just keep moving, keep L like incrementing to the right, keep R incrementing to the left. We can move both of them at the same time here because we have a match and we wouldn't need to increase the number of deletions here. But we also want to compare that to the case where we don't essentially take the bait, right? Maybe we might have a situation where sure, it would look nice. It would seem like, yeah, maybe we want to use these things, but it would be a mistake to do so. I don't know if we have a good example of that, but hey, it's possible, right? There could be a situation where taking these two characters and like matching them up and saying, yes, we want these to be part of our palindrome, that might not be optimal. What if we take one of these characters and then later we find, oh, actually there's a better way to do it. That might be a possibility anyway. I don't know, maybe if I thought about it more, I'd find that that might not be necessary, I'm not sure. Anyway, the point is, we want to look at these two possibilities, right? So basically, let's assume that they don't match. So in that case, we'll just say deletions is going to be assigned the value of 1 plus. And I'm saying 1 plus because one way or another, we're basically saying, okay, let's delete a character. So like right off the bat, in this case, we've got L, we've got S. These do not match. So we have two options for how we should proceed from there. We could either say, yeah, reject this L, we're not going to use that, move on to the I over here. Or we could say, reject this S, we're not going to use that, move on to the A over here, and compare that to the L at the start. One way or another, we're adding 1 onto the number of deletions over here. By the way, just to be clear, we're not going to be keeping track of like which characters we're deleting. We're not going to be keeping track of which characters remain. If this problem was asking for the actual resulting palindrome that happens, this would be a very different solution. So in this case, we're only going to be dealing with the number of deletions and that's it. So that's actually going to help us out a lot in terms of managing memory here. Okay, so going further, basically the idea is we're adding on 1. We know that for sure. What are we adding it to? Well, basically the minimum of the following two results. It could either be that we're calling our search algorithm with left plus 1 and regular R, or it could be that we're calling it with regular L and R minus 1. Now, is that going to be safe to do? Like, are we sure that that we're not going to go too far here? That like by doing an L plus 1, we're not going to go past the center, for example? Well, yeah, we're sure about that because the only time we could get into this block over here is if we've made it past these two already. And these two are basically the possibilities that either of our pointers were at the center. So there's no way either of them could be at the center before doing this step over here. Afterward, maybe. That's a possibility. But not before. Okay, so then we have to address the possibility that the characters are the same. in which case we'll say, yeah, this, if string at L is equal to string at R. If they're the same character, then we could also do something different. We could say, all right, well, in that case, let's compare deletions, the current value of deletions that you have right now. We want to compare that to the result that we'd get by doing another search thing, right? With L plus 1 and R minus 1, and we don't need to add 1 to this one the way we did up here, because in this case, the two characters match. So maybe I'll just put a comment. Do the characters match? You know, because that way we might be able to get a better way to do this. You know, we might be able to get away with fewer deletions this way. Okay, so that's basically our recursive step. Not bad. I mean, there's not too much to it, I guess. Basically, we look at the possibilities of, and let's make a comment here. Which is a better option? Deleting like string at L, or yeah, deleting the character, or I'll say deleting the left character or right character. Which one's a better option? That's what we're trying to figure out with this line here. Now, hey, just to be clear, we might delete them both, but we're just doing one at a time. So like, for example, we might say, you know, I don't really like the L here. Well, let's not use that. We'll move on to the next one. So that's going to be an I, but of course we're keeping R the same, so it's going to be S. Then when this fires again, because it is, you know, it's calling search again, and now we have a new L and R value, we then might say, actually, I don't really like this R. Let's move on to A, and we'll keep the I the same. So we might end up deleting both L and S. We're just not going to do both on the same step is the idea here. Let me give us a little more room over here just so we can see the whole thing. Okay, so we're going to be returning search, which is basically just calling this function. You can sort of see how like there isn't that much of a point to having this as its own thing, but you know, it's just a little more comfortable to work with it this way. I like the idea, and this is part of the reason I tend to prefer memoized recursion as opposed to dynamic programming. Or, you know, like the bottom up or whatever it is, you know, but the point is like the typical dynamic programming over an array, like this kind of stuff. I tend to prefer memoized recursion over that because it flows a little better in my opinion. Rather than sort of reorganizing the way we're thinking right at the very start, we're sort of starting with something very easily accessible, like a brute force algorithm, something that gets the point across in a pretty intuitive way, or at least relatively so. And then from there, we can sort of introduce the technology that's going to allow us to actually make it a viable solution, as opposed to just kind of like a brute force pipe dream kind of thing, right? Because like, I mean, spoiler alert, but this is going to time out. This is going through like every single possibility. It's definitely going to time out. Anyway, what we're doing with this stuff over here, this is kind of an optimization. I mean, like we could do this differently where we end up continuing the recursion in this case. But what I'm going to do is basically say this. So if we make it this far, if L meets the center, right? So like, for example, let me choose a good one. Yeah, okay, this is a good one. So we're basically working our way in from the left and from the right. The left pointer will meet the center pretty quickly, right? It's going to get to this point. And then if it gets here, and let's say the right pointer is still over here, you know what? Let's get the tablet out. Let's make this as visual as possible. It's probably worth it. Let's get another cool color in here, and we'll make this a little thinner, maybe not that much. Okay, let's try that. So yeah, basically this is what I'm saying. Like if we look at the F over here, we could say that that's what L is pointing to, and then maybe R is pointing to the E over here. Now, since the L has made it to the center, it can't go any further. That was meant to be a dashed line. But anyway, the point is it can't go any further. So the only hope is for R to kind of make its way over here. Now, the thing is, it's like in this case, oh, geez. Probably it wouldn't even happen this way. I think the R would make it there first, but we don't need to get into those details right now. The main thing is that we have an E, we have an F, we have an F. The only way this is going to work is if we find like, you know, a corresponding E over here and then another F. So basically, I guess I didn't choose the right example here, but what I'm trying to say is essentially that we would have to clear out all of this stuff over here, right? I guess here, okay, we're going to use a perfect example for this one. So it's actually just going to be this thing, but yeah, like that exactly. What was the answer here? 4, I think. Yeah, so it should be like this. Now, in this case, yeah, this is better. This is a much better example for what I want to point out here. So, okay. There we go. All right. So in this case now, L is going to get to this F over here, right? That's going to be our L pointer. And I guess we'll say the V is going to be where the R pointer is, because the idea is that we've moved them in because the E's matched up, right? So we're at this point now. L is at the center. So what do we do at this point? Well, we could basically just say like, okay, so L's already at the center. That means we got to delete everything in here. All 4 of these characters, well, and this one too, actually, I guess, right? So all 5 of these characters gotta go. But as it turns out, one of them is an F that can match up with this one. So this is going to be kind of our game plan. The moment we find that that one of these things has reached the center, we're basically going to take the other thing and say, okay, well, I'm going to assume I have to delete everything here, but then we'll just kind of walk this over to the center from the other direction, and we'll see if we find a matching character over here. If we do, then we can sort of reduce the deletions by 1 anyway. It's not going to be too major, and it definitely won't, like, there's no way we'll be able to reduce the deletions by more than 1, because otherwise we're kind of moving the center, right? So it kind of defeats the purpose of the problem. Anyway, so the way we're going to do this is we're going to start by saying deletions is assign the value of whatever we have at the right minus the center. Okay, it's the gap between them. It's that many characters. When we're looking at this one, we're comparing the F to the V over here. So this is like index 1 versus index 6, I guess. 6 minus 1 would be 5. That's the 5 characters that we'd be deleting. But then we're going to go ahead and search and say while R is greater than center, and we'll spell that as correctly as we can. While right is greater than center, we're going to say if string at right is equal to string at center, if we find a match over here. Well, in that case, we're going to say deletions minus minus, take 1 off the deletions, and then we're going to break. We're going to get out of this loop, because notice, we don't want it to happen more than once, right? We want to break, because otherwise if we didn't, what if there were like 40 other F's in here? We don't want to keep removing the deletions. It's just a maximum of 1. We can only have 1 of these things. We found one to match up in such a way that the middle element is like 1 of 2 middle elements, right? That's sort of the idea. So yeah, that's kind of a lot, I guess. It looks like a lot anyway. It's maybe not as bad as it might seem. But anyway, we're going to see something really, really similar over here. This is the case where the right index was the one to find the center. So in this case, we'll say center minus L, because we know that center is going to be greater than L. L wouldn't have made it there yet, because if it had, we would have already done this. Okay, so great. We're going to do the same thing from the other side. So, whoops, I missed one thing, which is that we actually have to say R minus minus. If we don't do that, then this while loop is maybe going to be here for a while. It's maybe going to be doing its thing for a while. So while L is less than center, we want to be doing the same sort of thing. Before I write all of this out, I want to point out a few things. First of all, we're doing this R minus minus. We could actually, on second thought, let's actually get this all written out first, and then we'll start talking about optimizations. I want to get to a point where we're actually passing like at least one test, I guess, and then we can sort of talk about what we're going to do from there. So if this is equal to this, then we're going to say deletions minus minus and then break. Okay, same thing. Okay, cool. And then we also have to do L minus minus, right? Yeah. Or L plus plus. Yeah. Cool. So that looks good, I think. Maybe. We'll find out, I guess. But just to sort of clear up some room over here, is there a way we can see it all in one? Jeez. Maybe if we delete all the comments. That's a good idea, right? Okay, so I think we can see enough of this for it to make sense, hopefully. So just as kind of a review, we have this function called search. It's something that we're calling and returning the result of, and that's going to be it. It takes a left and a right pointer as its arguments, but because these are like optionally provided over here, since they have default values, Yeah, we don't need to provide them. We can just call this with an empty thing. Okay, so continuing over here, basically the idea is we say let deletions be assigned the value of 0. We don't know how many there are going to be. We don't really need to even say it's going to be assigned the value of 0, because something you might notice is that in every case here, no matter what path we end up following, we're assigning a value to deletion. So I think I might actually just say let deletions. In that case, you might be wondering, why wouldn't you just say let deletions in each of these things? And the reason is because we're doing return deletion. So keep in mind with this ES6 syntax, like using let or const, it's block scoped. So it's more than just the regular scoping we might be used to with var, where it's scoped essentially to the function that it's contained in. In this case, with a let, if we put the let in here, we wouldn't be able to access that variable outside of that if statement or whatever kind of block we're dealing with, whether it's like a loop or a conditional or, you name it. But anyway, the point is, and definitely a function. Anyway, continuing from here, we initiate deletions, right? We instantiate it. Is that the right word? Anyway, the point is, so if left is center, if right is center, these are our base cases. These are like what we do when we get there. So like if you're thinking about a typical recursive algorithm, normally, for example, if we had like factorials or something like that, actually that could be fun, right? Let's go ahead and do that. So function factorial, just to give us something to kind of compare to. And we'll start with num over here. So what we want to say is if num is 1, or if num is less than or equal to 1, I guess, we're just going to return 1. Otherwise, we're going to return num times factorial at num minus 1. Okay, so we have a base case and we have a recursive step. That's sort of like the foundation of recursion over here. Base case, recursive step, yeah. It's kind of like if you've ever studied math and looked at like proof by induction, it's very, very, very similar. It's the same sort of principle. We basically have like, the smallest building block, I guess, and then we find a way to reduce everything to that kind of building block. Okay, so that's factorial. It's very simple compared to something like this, and we're not actually going to use this. I just wanted to show it to make it easy to sort of make comparisons here. So in this case, the main difference is that all of this stuff we see here, that's our base case. Like all of this can be compared to this one line over here in terms of what it's doing, right? Because this is basically saying, oh, okay, like let's not do any more recursion because we're almost there. We can finish up from here. Whereas in this case, we're saying, no, we haven't actually like got to the point that we're trying to yet, so let's keep this going. So what is the recursive step actually doing? It's basically saying like all the possibilities, it's saying, well, if these two things match, like if these are the same character, then let's just pull the indices toward each other. Left goes to the right, right goes to the left. Otherwise, we're basically going to say, well, we got to delete one of these things. They don't match up, so let's see which one's better, which is the better deletion. Now, something to keep in mind is we're not just looking at this one particular case, in the sense that when we say math.min of search this versus search this, each of these search things is going to be like many, many calls to the search function. Like this is going to keep going until it gets to one of these base cases in the exact same way that something like this is going to keep going until it gets to this base case. So if num is something like 15, then it's going to keep going. It's going to go through 14. It's going to go through 13. It's going to go through 12, all the way down to 1. So basically that's what I'm saying with this over here, that it's not just comparing two numbers. It's comparing, well, it kind of is, but those numbers are not that easy to get to. It's not just going to call search and then get a number and be done with it. Like this is going to call search, which is then going to call search again, which is then going to call search again. Like many, many times this is going to happen before we actually get the final result here. Okay, speaking of the final result, should we actually go ahead and do that? I'm going to delete this thing, I guess, for now, because we're not actually using it. It was just there for the purpose of comparison. But let's actually run this thing, and what I'm expecting to have happen is for this to pass some of the tests, unless there's some sort of syntactical error or something like that. Yeah, okay, so it's passing this test over here. It's passing 18 out of 43 tests. 43 because we added this one. There are actually only 42 provided in the test suite over here. But you'll notice that all the way up to 17, like it's getting them right. All the ones that it actually was able to complete, it's getting them right. So 18 is the, well, hold on. Yeah, so it's getting that one right. 18 is the first one where it's saying, empty, I don't know what to do, it's too many letters. So yeah, I don't blame it. But anyway, the point is the center's 30 in this case, we should have to probably remove 30 elements. So let's see if we can find a way to grapple with this time limit exceeded issue. I don't think anyone here who's seen these streams before is going to be too surprised by what we're going to do here, but the main thing is, well, actually, hold on. First of all, because we know the code's actually running and that it's giving us the result we're looking for, I want to kind of simplify this a little bit. So the first thing I'm going to do is say, well, we're using R and then we're de-incrementing it. So we might as well use an R minus minus here. That way we don't have to use these extra lines and we can kind of tighten it up a little bit. I don't know if this is generally good practice, but it's efficient, right? Now, don't get this confused with like a minus minus R or like a plus plus L, because that would increment first and then use the resulting value. That's not what we want. We want to use the value as it is, and then we want to alter it afterwards, maybe, right? If we end up using it again. We might not, in which case it doesn't really matter how we altered it. But anyway, so that's one thing. The other thing is this while loop over here doesn't actually have more than one line. So we can do this kind of deletion over here. In fact, we could even just bring the if right over there if we wanted to. It looks a little awkward, but I guess that's not going to stop me. So yeah, maybe we'll just pull those in. I actually don't even know if that's proper to do. Maybe it'd be better to keep them like that. Yeah, it just looks so weird. Anyway. Okay, so this is good in the sense that it's all kind of fitting here now, but it's also not good in the sense that it's, not working, not actually passing all the tests. That part's not exactly ideal. I guess one thing we can do while we're here, if we're trying to like sort of compress this, instead of doing this, we could actually just like put this whole thing in one of these and then call that. And just say return, that, right? This should basically give us the same result, I think, unless I committed some horrible mistake. Yeah, we're fine. Okay, so because of this is basically telling us we can just sort of take this stuff and put it up here, and now we'll call kPalindromeWithCentre instead of calling search. Okay, so I'll just copy this from here because we got a bunch of searches here that are not really as relevant anymore. And we don't need this anymore because we deleted that first line. In fact, we don't even need that. What we do need to provide is the string and center part for each of these. So this is definitely getting a bit longer in terms of these calls over here. And that's not even going to be the end of it. So let's get, okay, come on. There, good. Good job. Okay, yeah, that's fitting really well now. Is it actually working? That's probably worth asking. Let's find out. Yeah, as well as it did before. Anyway, this is where things get kind of interesting because at this point we have the right idea, you might say, right? We sort of have this idea that is working, that's like performing the right steps, I guess, but it's just way too slow. And part of the reason for that is because it's repeating the same calculations. Where was it? It was somewhere in here. They kind of define this. Optimal substructure, which means the problem can be broken down into smaller, simple subproblems, which can be broken down into yet simpler subproblems, and so on, until finally the solution becomes trivial. And it also has overlapping subproblems. That's the part that's going to allow us to do this next thing that we're going to do, which, I mean, honestly, I've done this so many times now, but it still just feels exactly like a magic trick. It's just a magical thing. So, you know what? I'm deciding that these are bothering me so much that I'm going to de-indent them. Yeah, sorry if it's not proper, but, oh, geez. Okay, cool. So, yeah, we're going to memoize at this point. We're going to pull that classic magic trick of memoizing. So we're going to pass this another variable. It's going to be called memo. And even, I guess, before all of this stuff, we're basically going to use this hash value. Why a hash value? Well, because left and right might be different, right? And we essentially want to treat each of those situations as a different scenario. So it's only if left and right are equal to each other that we consider that a repeating, like overlapping subproblem, one that we've seen before, right? It's only if L and R are the same as one that we've seen before. So how are we going to keep track of that? Well, basically, we could just do something like this, like 1e6, in other words, 1,000,000 times left plus right. So in this case, we're basically taking both numbers and we're adding them together, but in such a way that there won't be collisions. Because something we'll notice over here is that the length of the string is going to be only as great as 1,000 anyway. So doing something like this is totally safe in the sense that like we're going to even have a bunch of zeros in this. Like we could tighten this up a bit, but no need. It's probably fine like this. Okay, so that's our hash. What do we want to do with the hash? Well, we basically wanted to say something like this. If you've seen it already, like if hash is in memo, then we'll just return memo at hash. Well, how could that be? Well, I guess it means we need to sort of keep track of them, right? So at this point, we'll say hash at memo is going to be assigned the value of deletions, right? This value over here, this result that we would normally be returning, we're going to say, wait, hold on a sec. Stop. Before you return this, remember it. Don't forget this experience. You don't want to have to do all of this stuff again. Remember it. Remember it for next time. That way you can just get to here and be done. So remember it. Memoize it. Memorize it. Remember it for next time. That's basically the idea. So if we do this now, what we're going to find is that just like before, it's actually going to time out and we're not going to pass all the tests. And the reason is because it's looking at this and saying, memo? Oh, you know what? I didn't get a memo. So I guess I'll just make this an empty thing. I'll make it an empty object. Hash is in memo? No, of course it's not in there. It's an empty object. Why would it have this thing in it? So this is essentially no different from what we had before. What we need to do is put memo in there. And that way, it's going to remember it. It's going to pass this along to every other call. So that every instance of kPalindromeWithCentre, every call to this function will know what we've seen before. That's a pretty cool thing, right? I guess it's kind of like what writing books is like, for future generations to remember what you learned and to not commit the same mistakes. Okay, so what are we finding here? It's not working, and that's kind of interesting. Why would that be? Well, maybe it's this here where we're saying hash at memo instead of what we should be saying, which is memo at hash. I'm not even sure how that was working. Like, it would be interesting to do a console log on that and seeing what it was actually storing, because that's kind of funny. All right, there we go. That's more like it. I actually make that mistake a lot, and it's taken a lot of time to find it sometimes, so that's got to be a record. Look at this. We're passing all the sample tests. We're passing all the hidden tests. If we were to submit this right now, we'd get the big correct. This is an exciting time. So, basically, this is a good example of a memoized recursive algorithm. The big advantage I find to this type of algorithm is the idea that we can start with something that just looks pretty like plain text. It looks like something that we can follow relatively easily. And then we can just kind of, like, without much trouble, we can augment it with this extra bit of technology. This is like, putting on the exoskeleton, putting on the Iron Man armor kind of thing. So it's taking this regular algorithm and making it superhuman. Super algorithm. Anyway, the point is, so now this is like just not having any issues passing the test. If we run this, it's just saying, oh yeah, I remember all that, like it was yesterday. So memoization can go such a long way. Now, again, like I said before, we could use a dynamic programming strategy here. We could use like the two-dimensional array, and there's nothing wrong with that. I mean, that's a great strategy. It's a good one to use. If you find that to be a more intuitive way to do it, then I definitely encourage it. Personally, I prefer this kind of strategy for the aforementioned reasons, but hey, it's completely up to you. I'm not going to attempt the other type of solution. I mean, there are a few other ways we could probably try to do this one. Like, for example, like I was saying before, starting at the center and working outward from there. But this is probably fine. So I guess we'll just submit, make sure we get the big correct. Yeah, we'll confirm that. And okay, cool. We see the big correct. Everyone's very happy, and it's good. Okay, so geez, is there anything else we want to do? I don't know. Anyone have any requests or anything like that? I think that's probably it for this. I think that's the only thing I really wanted to say about this. Like, we've got our solution now. So unless anyone has any other questions, comments, or concerns, we might actually just wrap it up there for today. Geez. Well, I guess one thing we could talk about would be like time complexity, space complexity, that sort of stuff. It gets a little murky with the memoization, but I guess let's think about it for a minute. Like, if we didn't have the memoization, we're basically looking at like every possibility, maybe a bunch of times, right? Like we'd look at the left, and then with this left value, we would consider every single other right value. And then with this left value, we consider every single other right value. I feel like it's maybe more than just that though, because like, okay, like if this one is here and this one is here, for example, then going from there, we're gonna make like a bunch more calls here. I guess there's actually a very simple way to think about this. We're calling kPalindromeWithCentre at least 2 times for each character, right? Like that's, yeah, we're calling it at least 2 times for each character. So I guess we could say that the complexity, the time complexity would be exponential. It'd be like 2 to the power of n, where n is the number of characters here, the length of the string. But we kind of fix this with the memoization in the sense that I think we make it kind of quadratic, right? Because like the left, yeah, now for every character, since we're not repeating calculations, this could be, well, actually like less than the length of this thing, but you know, something related to the length of the string. Like for every character, we would have at most at most the length of the string minus 1 other characters to look at. So because of that, we could say, yeah, it's probably down to quadratic, big O of n squared, which is just so much better than 2 to the power of n. Like I can't emphasize enough how much of a savings that is. Like, okay, hold on a minute. Let's say f of x is going to be 2 to the power of x. Now this is a very fast growing function. So I don't know, maybe we should like zoom out or something like that. Hard to say. But anyway, we'll say g of x is going to be x squared now. Okay, so here's something to keep in mind. We look at this and we say, oh yeah, look at that. Start like the quadratic's a bit below the exponential, but it soon overtakes it. So I guess the quadratic is actually the worst one because it's taking more time than the exponential. So if we were in this range over here, where it's like between 2 and 3 in terms of the size, like if the string was of length 2 or 3 or something like that, then yeah, we'd maybe the exponential one's better. Maybe it's better not to use the memoization in that case because it's like taking up extra memory. But if we keep this thing going, and yeah, maybe I'll adjust the y-axis to sort of show us more of this stuff, what we find is that it doesn't take long. Like by the 5, they're pretty close, all things considered. They're actually not that close. Like this one's at like 32 and this one's at 25. I guess they're pretty close. Anyway, the point is, it doesn't take long. Like by 10, there's a stark difference. Like this one's at 1,000, the quadratic one is at 1,000. This one, the quadratic one's at 100, the exponential one's at 1,000. That's only for a length of 10. Remember, our string could be of length 1,000. So, like, it's not even a question. Like, I can't even find the top of that thing. This is, like, yeah, these 2 functions are in totally different leagues. Like, if we look at, let's do g first. G at 1,000. Whoops, that's g at 100. G at 1,000, we get a million. A million operations, it's a lot, but it's doable. If we look at f at 1,000, it's like, I don't even know how to express this number to you. This is like, imagine you got 1 and then 301 zeros after it, and that's not quite as big as this current number that we're looking at here. It's not even like a comparison. This is way too many operations. Like, I don't even know how I would say this number. Yeah, this is like a Google cubed. Right? Like 1 with 100 zeros after it, a Google. It's like that cubed. Like that's huge. That's way, way, way too much. This has 6 zeros. This has 301. It's way too many. Okay, so the point I'm trying to make is like, it might seem like exponential and quadratic, like, I don't know, they're both curves that kind of go up in a nonlinear way, but there's such a huge difference. Like, yeah, they're not even in the same league. So the fact that we're able to sort of economize and change something that's like an exponential complexity into a quadratic complexity, that's huge. That's really, really good. Yeah. Now, there is a bit of a trade-off, but actually it's hard to say how much of a trade-off there would be, because I was about to say that there's like a memory trade-off in the sense that this memo stuff is gonna take up some room. I mean, no doubt about that. It could take up a fair bit of room. But then again, so could the call stack, right? Like the memory that takes up. So yeah, I don't know. That's like getting right into the nuances of it. I don't know if I'd have the expertise to even begin to discuss that. But anyway, the point is we get huge, unimaginably meaningful savings just by adding on this extra bit here. Well, actually, hold on. Let's take stock of how much of this is actually the memoization. Because I think, yeah, we haven't really done that before, and that would be kind of a useful thing, I think. And then that's probably the last thing we'll do, unless anyone has any questions, comments, or concerns, or something else they want to look at. But anyway, you'll let me know, right? Okay. So basically, for the memoization stuff, what we're adding on is this thing. So we're adding on this memo. We're adding on this stuff with like all this hash business. That's happening right here. That's part of the memoization. These two things right here, as well as this guy, that's part of it, because otherwise we're not passing it in, and it's just going to use an empty object every time. And then this over here, and let's make sure we get those words in the right order, that we say memo at hash and not hash at memo. So when you compare this, like the stuff that I just circled over here, to the whole algorithm, like all this other stuff over here, oh, this is minuscule. Like the main brains of the algorithm have been unchanged. Like everything in terms of how it's working, everything in terms of like the thought process behind it is unchanged. It's exactly the same as it was before. The only thing that's different is it's saying, oh, I actually maybe remember this for next time. And then, you know, ask yourself, have you seen this before? So yeah, anyway, that's pretty much it. I'm actually even surprised at how little this is. Like, it's really not that much. And especially when you consider that it's the difference between this and this, like, it's probably worth it. Anyway, okay, I guess that's going to be it for tonight. Thank you so much for tuning in. It's been such a pleasure. Let me know if you do end up having any questions, comments, or concerns. You can reach me, I guess, here on the Twitch platform, or as well as codesignal.com. My screen name is ZeroCool, so feel free to send me a message. Don't get confused with the imposters. Anyway, yeah, I guess that's it. So thanks for tuning in. Have such a great night. Remember to believe in yourself. Anything's possible. I love you all very much. I'll see you again soon. Bye.